A swarm on a tree branch is not a miracle of nature. For a layperson, it is a fascinating sight. For a systems engineer and apiary operator, it is a critical system failure. It is the sound of your capital leaving the base. The loss of a swarm does not mean only the loss of biological hardware. It means the absolute loss of the main nectar flow and weeks of delayed work. Your operational cost, OPEX, remains the same, but your capital realization, CAPEX, drops to zero. Most beekeepers see swarming as a force of nature, as something that simply happens. That is an amateur approach. The truth is exact. Swarming is not chaos. It is a highly structured biological process. It is an expansion algorithm deeply embedded in the genetic code of every worker unit. Bees do not leave because they are unhappy. They divide because they follow a perfect mathematical pattern. Today, we will not talk about the useless tearing of queen cells. That is fighting consequences, not causes. Today, we will surgically decode this algorithm. We will understand the exact triggers that activate the swarming impulse. We will learn how to hack their biological software before the system decides to split. If you want full honey supers instead of empty brood chambers, follow this mathematics to the end. To prevent collapse, we must understand the input parameters. A bee colony is a superorganism. That organism continuously processes data from its environment. Swarming is a software response to three specific conditions. This is the swarming triad. 1. Drop in pheromone concentration, queen substance. The first trigger is chemical. The queen continuously emits a pheromone that worker bees distribute throughout the entire system through trophallaxis, food exchange. This pheromone is the signal that the system is stable. When the population grows exponentially, the distribution network breaks. The signal becomes diluted. Bees on the periphery of the hardware stop detecting the queen. The brain of the superorganism records an error and triggers the first alarm for replacement or division. 2. Demographic imbalance, protein pressure. We enter the phase of spring expansion. The queen delivers 2,000 eggs per day. At one point, a massive army of young nurse bees emerges. Their hypopharyngeal glands are hyperactive. They require open brood to consume the royal jelly they produce. If the queen is blocked and there is no open brood, the system experiences biological pressure. Excess royal jelly accumulated in young workers directly provokes the construction of queen cells. The processor now has surplus labor with no assigned task. 3. Resource congestion, brood chamber blockage. This is the most expensive human mistake. Spring nectar and pollen intake is massive. Foragers do not have adequate storage space in the accumulation zone, the honey supers, so they deposit fuel directly into the reproductive zone, the brood chamber. A honey cap forms that physically pushes the brood downward. The queen runs out of empty cells for egg laying. The algorithm makes the final logical decision. There is no space, we divide the system. Biological software always signals its intentions. You must know how to read the code. If you open the hive and see capped swarm queen cells on the bottom bars, the game is over. At that point, you are not preventing swarming, you are performing damage control. Early indicators require precise observation. Phase 1. Construction of drone hardware. The system first increases drone production. Drones are logistically necessary to fertilize the new queen. Their incubation period is longer, so the system starts their production weeks before the swarm itself. Phase 2. Polishing of queen cups. Empty cups appear on the lower edges of the frames. If you observe young workers aggressively cleaning and polishing the inside of these cells, the algorithm is gathering data to initiate reproduction. Phase 3. The point of no return. Detection of an egg in the queen cup. At this moment, the system changes its operational mode. The queen drastically reduces egg laying in order to lose weight and become aerodynamic for flight. Foragers stop nectar intake. They form beards at the hive entrance. Production is officially halted. Detecting these parameters in real time, at 30 degrees Celsius, while operating among thousands of individuals, requires strict systematization. You cannot rely on memory. In industrial engineering, we use protocols. To standardize your process, I created a precise spring inspection and swarm prediction checklist. It is an exact protocol on a single page. It defines critical indicators of system decline, optimal time intervals for opening the hardware, exact values for detecting brood chamber blockage. This checklist is available completely free. The download link is in the description below this video. Print it. Keep it with your field equipment. Do not make decisions based on assumptions. Make them based on quantified data from the checklist. Now that you have the diagnostic tool, we move to physical intervention. How do we break the loop? You must deceive the biological algorithm. You must simulate the expansion the system demands without losing actual workforce. These are 3 strict operational protocols. Protocol 1, thermodynamic unlocking of the brood chamber, space management. Adding an empty honey super above the queen excluder is not enough. Space must be integrated directly into the reproductive zone. Isolate the 2 outer frames with old honey and bee bread. Remove them from the system. In their place, directly next to the brood, install foundation frames. This is an engineering trick. Young nurse bees now receive a task. Wax synthesis and cell construction burn their excess energy. Protein pressure in the system immediately drops, and the queen receives the necessary space for continuous egg laying. Protocol 2. Physical division of the system. Nucleus formation. The safest method to stop swarming is to artificially perform the process. You operate like a surgeon. Remove 2 to 3 frames of capped brood together with the covering bees and transport them into a new hardware unit, a nucleus colony. With this action, you achieve 3 objectives. You eliminate demographic pressure in the parent colony. You physically free space for new queen operations. You create a backup system, a new operational unit in the apiary. Pure economic benefit. The base colony detects the loss of mass and shuts down the swarm algorithm. Protocol 3, vertical separation, Demaree method. This is an advanced protocol for macro optimization of yield without physically dividing the bees. The entire biological software, the brood, is moved to the uppermost box. In the lower box, the main brood chamber, you leave only the queen, 1 frame of open brood, and empty foundation frames. Between these zones, you install empty honey supers and a queen excluder. What have you done? You reset the pheromone distribution. The queen now operates in a vast, empty space. The young workforce is isolated at the top of the system. The swarming algorithm is instantly and permanently interrupted, while the entire foraging army remains intact for the main nectar flow. The system does not forgive mistakes. Even when applying protocols, operators often collapse their own production through 3 fatal errors. Error 1, delayed logistics. If the system already has capped queen cells, adding foundation frames is wasted money. The swarming impulse is dominant at that stage. The biological software is locked. Only radical physical division of the colony can help. Error 2, thermodynamic collapse, poor ventilation. A bee colony maintains strict homeostasis at 35 degrees Celsius. Summer temperatures and poor ventilation exponentially increase thermal stress. High temperature physically accelerates the swarming impulse. You must open the ventilation screens on the bottom boards and remove winter reducers. Allow the system to cool itself. Error 3, obsolete hardware, old queen. Systems operating with queens older than 2 years have a 70% higher mathematical probability of collapse and swarming. Why? Because an exhausted queen physiologically cannot produce sufficient quantities of pheromones, queen substance. Regular replacement of biological processors, queens, is not optional. It is the fundamental mandate of preventive engineering. Preventing swarming is not a romantic battle against nature. It is the strict redirection of biological energy from the hardware toward your economic objectives. You are the system operator. Your role is not to observe, but to intervene at the exact moment. Control space before the system reports an error. Employ the excess workforce. Monitor the parameters from the checklist. If you properly manage thermodynamics, demographics, and resources, the probability of swarming falls below statistical error, and your CAPEX during the main nectar flow reaches its maximum. With this, we close the analysis of the expansion algorithm. If this surgical deconstruction of biological software brought you quantified value, click the button to follow this channel. Activate notifications. This is only the beginning. In the next episode of this series, we move into total offensive mode. We will cover radical system merging protocols. You will learn the surgical methodology for revitalizing collapsed colonies and recovering lost workforce immediately before the main nectar flow. Download your operational protocol from the video description. Apply the mathematics. See you in the next report.